So the next type of modeling is hierarchical regression equations, which is a hybrid model. It combines both log models and linear models. So it is a better predictor compared to log or linear models. There's a reason behind it. Because in log models, you use the both categorical and metric data, but they may not be like all the categorical variables together. You cannot sum up or you cannot put it into equation. But here in hybrid models, you can choose the data sets which you want to combine separately with the log modeling. And also you can combine those categorical data with metric data. So, which means that here you're developing a hybrid model, including both log and linear, including both metric and categorical data. So, obviously, with any patient's data set, you always have categorical data and numerical data. For example, gender, male or female, is a categorical data. The white cell count is a metric data. CRP is a metric data. Anastomotic leaks, number of anastomotic leaks, is a metric, discrete metric data. So if you want to combine all these type of things, even like for example ASA grades is a categorical data, ASA1, ASA2, ASA3, ASA4, ASA5. So if you want to combine all these types of data into one hybrid model, you can only do with hierarchical models. So hierarchical models are better predictor models than linear or log models.
Sorry to interrupt. Is the hierarchical model the best one to use? And what makes it better or worse than the others?
That's a very good question, Sonia. See, in real life, you never get the data sets purely metric and purely categorical, right? So you'll have combination of the data sets. So you'll be having lots of categorical data, lots of metric data. You may have to analyze all of them together. So what happens in the log modeling is, unless there is a big rise in the X values, it doesn't reflect on the Y. So that means that the log models lack sensitivity, right? So whereas if you use hierarchical models, hybrid models, which combine the various similar characteristics of data together as a single set, and it will test against another set of variables and to see how they interact with each other. So we can measure the R-square change from one model to other. So which is possible only through hierarchical model because they are very sensitive and advanced.
Is hierarchical just a combination of linear and log, or is it something different altogether?
That's a very good question, Sam. You know, it appears mathematically that you're combining the metric data and categorical data, so you're using both log and linear models, right? So, but in reality, in real life, when you use hierarchical models, it's not simply between combination of categorical and metric variables. It's a combination of the sets of variables which have similar characteristics. Like for example, comorbidities like diabetes, hypertension can be combined together as a one set, whereas risk factors like smoking, alcohol can be combined as one risk factor for mortality to see how they affect. So you can see how the hypertension and diabetes interact with smoking and alcoholism, and what is the R-squared change. You can measure it. So here we are seeing the interaction between various comorbidities and risk factors, covariates and explanatory variables like low albumin or something else which you measure. So you have a chance to play between sets of categorical variables and sets of numerical variables same time, and to see if you drop one variable or one set of variables, what happens to the model value or what happens to the function change. So this is why hierarchical models are real-time models, and also it will give you an insight about in real life what happens with the interaction of various factors, various variables on the Y outcome measure. There is a disadvantage with hierarchical models. You need a larger data sets and you need both categorical and metric variables. And also you need a data with a large number of patients, which means that smaller data sets cannot be considered for hierarchical modeling. And also you need to understand what are the predicting variables, what are the explanatory variables, what are the covariates with prior knowledge. For example, you need to understand that the low albumin is a risk factor for anastomotic leak. Unless you have the prior knowledge, you cannot be labeling that as an explanatory variable. So a predicting variable could be simply an anastomotic leak can lead to death, but the explanatory variable could be low albumin leading to mortality. So a prior knowledge is important for hierarchical models. So which are the predicting, which are the explanatory, which are the covariates, which are the dependent variables. So one need to understand the subject thoroughly. You need expertise before you run hierarchical modeling. I'm going to give you an example data set. So look at this data set. The hierarchical data sets are very complex. You can see lots of columns. So first column you have author, and next column you have year, and total number of participants reported in that paper, and number of patients died after surgery, and then number of males, number of females, which are part of the analysis, and also number of patients who had low ASA grades and number of patients who has got high ASA grades. So this data set has got multiple variables, both categorical and metric variables. So that means that if we wanted to look for any causative factors of mortality, we are looking for assessing both metric as well as categorical variables together to see what impact they have on the mortality if you consider mortality as the dependent outcome measure. So this is how the hierarchical data sets look like. You need a larger data sets. So before I run any statistics, I wanted to emphasize 4 key things. In a hierarchical equation, you have 4 key things. One is R square, which is the model value, or the how good is the model, and then R square change, which is nothing but the difference between model 1, model 2, and other models, and then function change, whether the R square change is significant enough or not, it will decide. And then finally, whether the overall model has significant value or not, or whether the function change itself is significant or not, we can calculate the p-values as well. So there are 4 key statistics. Number 1 is R square, number 2 is R square change from model 1 to model 2, and then function change, and then p-values for both models as well as R square change.
Mr. Opara, you were explaining about R squared change. Is this the difference between R squared values in model 1 and model 2?
That's exactly correct, Sonia. So when you do hierarchical modeling, you construct various models between various variables, like you combine similar kind of variables together, and let's say you got few similar variables in model 1 and you add different sets of variables in model 2, and you get, let's say you got 80% as a model fitness or model equation value, as a R square value as 80% or 0.8. And if you get similar kind of value or even more, let's say if you add model 2 into that, and you get 90% or an increment in the fitness or increment in the model value itself, which is R square. So there is a change from 80 to 90% or 0.8 to 0.9 in the R square value. That is nothing but R square change. So anything above 5% change is a significant change. So that means that by adding set of variables for model 1, by adding model 2 to model 1, you are actually getting a better fit or a good fit model in predicting the Y as an outcome measure.
So this might be a silly question, but obviously you've been talking about function change. Do you mind clarifying what function change actually is?
That's very good question, Hassan. So hierarchical models measures function change, which is very important. What is a function change? So here you wanted to see how between each model, model 1 to model 2, what happens if you add model 2, model 3. So what happens to the R-square value, and also what happens to the mean of the outcome measure, and also is there any significant change within the variable from data sets like data points like from patient's data of first patient to patient data of 8th patient. Is there any difference when there is an intervention or when there is an interaction between the various variables? So a function change will be determined by looking at the actual outcome measure. When there is a big jump, when you add, for example, for model 1 you add another intervention as a model 2. So if there's a big jump in the outcome measure along the column or along the row, it will reflect as a mean of the outcome measure. That is what is a function change. It's not R-square change. So I'll give you an example data set. Here is an example of function change. In this, there are two equations here. You can see on the top model 1 and on the bottom there is a model 2. So you can see the dependent outcome is mortality and the independent variables are male gender and lower ASA, ASA1 and ASA2 in the model 1 equation. You can see the R-square value of that equation is 0.72, which means that 72% model value. And then you can see the model 2 when I'm adding ASA3 and above, ASA3, ASA4 and ASA5, the function change is significant, which is 41. And also you can see there is a big jump in the R-square value in the model 2. So you got now the new R-square for model 2 is 95%, which is 0.95. So there is a R-square change from 72 to 95, sorry, 0.72 to 0.95. And also function change between model 1 and model 2 is a 41. And that is reflected in the bracket as between 1 and 8, which means that there is a big function change or the outcome measure change between the outcome measures from first data set to 8th data set. Am I making sense now? There is a function change as well as R-square change between model 1 and model 2. That means that the model 2 is a better predictor than the model 1 regarding mortality, because the higher ASA in reality is a better predictor of mortality anyway.
So I have a question. I understand you have R-square and also adjusted R-square. So what exactly are you adjusting for and what's the difference between both of them?
Rich, that's a really important question you asked. What are we adjusting here? So, very good question. So, as I said, R-square is nothing but the model value, right? So, in a perfect square, so if there's a linear relationship between x and y, and if there's a positive slope, if the line is started from there, and if R-square is 1, it will linearly increase all along the line like that, and you get a perfect square. That means that R-square is 1. So, but in a perfect square, the R-square is 1 because all the data points, an increment in x is leading to an increment in y, an increment in x is leading to increment in y similarly, and they all are connected with a straight line all the way through. But in real life it doesn't work like that, right? So what happens is some data points are not connected, so there is a residual error. So how do we account for residual error? So this is what is adjusted R-square is. Like for example, if the same square rectangle you divide it into 4 quadrants and now redraw the line again to cover most of the data points. So let's say from this end the line for if this, as we divide it into 4 quadrants, so let's start with the first quadrant here. So the first quadrant line may appear like this and the second quadrant line may appear like this. and third quadrant line may appear like this, and the fourth quadrant line may appear like that. It's not straight line anymore. You see that? So it's a jigsaw line, but it's a perfect fit, quadrantic fit we call. So when you try to do a perfect fit with like a quadrantic fit, obviously it is not a rectangle anymore. You got ups and downs. That means that you're adjusting for error. That means you need to subtract the model value. So automatically it will go down. I'll show you the example again. You see the example which I gave you just now has got an R square value of 0.72. And then the adjusted R square is 0.66 in the model 1. Similarly in model 2, the R square value is 0.95 and the adjusted R square is 0.93. So, which means that when you adjust for residual error, there is a reduction in the model value or fitness. Am I making sense?
So Mr. Apara, just a quick question. You said that there were two p-values in the equation. Is there any simple way to explain exactly what they are?
That's really good notice. You have noted very well that there are two p-values in this equation. That's really interesting question as well, Jitesh. So the first p-value is to look at the model statistics like R square value. Here the R square value is 0.72 in the first equation and adjusted R square is 0.66. So which is significant because you see the p-value is 0.0032, is that correct?
Yeah.
Which is significant for that model. So as you add more variables into equation, when I add ASA 3 and above, you got model 2 in the bottom equation. And also underneath that there is something called F, which is nothing but function change, which is about 41 plus, which is quite big jump, so big number. So which is also significant. If you look at the p-value for function change for the F, it will be 0.0001, 3 zeros followed by 1. So which means that it is significant function change. So first p-value represents the model statistics, whether they are significant or not, and the second p-value, which is on the bottom of the equations, reflects the function change, whether it is significant or not. So which means that by adding an extra variable, which is ASA 3 and above, there is a significant function change in both R square as well as the outcome measure itself. So that's why the two p-values, if they are significant, that means it's a good result. There is a R square jump as well as function change, which is a good result.
What does root MSE actually mean?
That's a very good question, Sam. Root MSE. MSE abbreviation stands for mean square error, root mean square error. What does root mean square error exactly mean? So for example, if you want to plot a graph between x and y, x as an independent variable and y as a dependent variable, let me show you. So all the x points are here, all the y points are here, data points. So x1 comma y1 is here, x2 comma y2 is here, x3 comma y3 is here, x4 comma y4 is here. So the dots are all over the place. You want to draw a straight line, linear fit line. You can't draw it because it will go through, it doesn't connect, only probably connects first point and last point. It doesn't connect these 2 points. x2, y2, x3, y3 doesn't connect. How do you assume that the line should go in the center? So the only way to do is, you calculate the distance between the this and that, so and between the line. So you calculate so let's say arbitrary line goes like that, the distance between x2, y2 and distance between x3, y3 and the line, you calculate them. So you actually square the values, add them, and you take root mean of that, square root of the mean. So when you take the square root of the mean, that determines the point where it falls between x2, y2 and x3, y3, and it falls right in the center between those two. So the line has to go like that. So the more the distance between x2 and y2 and x3 and y3, the more the error. And the less the distance, less the error. So, and if they fall right onto the straight line, zero error. So, a best fit line which has got R square value has got root mean square error 0. The bad fit models have got more root mean square error. Am I making sense?
So, Mr. Bora, just a quick question again. I just wanted to know, when do you use which data? So, are there any computer systems that can do this automatically, or do you just have to do it manually every time?
That's a really interesting question, Jitesh. So, there are only limited softwares that can do this function of hierarchical regression or hierarchic function. So, I'm using Stata software, and it has got inbuilt hierarchic function. So, not every software you can have this function. So, not every software contains this hierarchical modeling. So, it is in the Stata and those built on the C language has got hierarchical or hierarchic functions.
Yeah, so if we subscribe to these bundles, will you be doing more teaching on how to analyze the data set using those equations? So we can just get a few more examples.
Yes, definitely, James. If you subscribe for our advanced bundles, where we taught you about how to analyze the data, how to interpret data, definitely we will also teach you on the live data set. So let's say, for example, if you're doing some project on the breast cancers, and where you want to see the correlation between NPI scores versus oncotype DX, then we can actually do a live demo to show you how to do correlation, how to do linear regression, and how to do logistic regression, and how to construct hierarchical models. And you'll have first-hand experience with us. If you have a data set that needs analysis, definitely we'll take you through from scratch to the end.
So while we're on the topic of hierarchical modeling, are there any papers you would recommend just to help me get a bit more background on the topic?
That's a very good question, Hassan. We have published this paper. If you have Google option in front of you, if you log into PubMed and if you type hierarchical regression and Mr. Uppara, my surname, you will see an article with the title Hierarchical Regression is a prediction of mortality while performing emergency laparotomy, as a title of the article. I'm the senior author on this, and this is the first paper we published on the hierarchical regression modeling.
Oh yeah, I found it. Thank you. I'll definitely read that later. Thank you.
Very good.
Can you show us an example of hierarchical modeling and how it works, please?
Yes, definitely, Ruj. So I showed you the data set earlier, right? Which I constructed these equations. So I'm going to take you through a demonstration so that you can solidify your understanding. I hope you all enjoyed my demonstration, guys. Thank you very much for attending my lecture today. We'll see you in future ISAP tutorials.
Yeah, no, thank you so much, Mr. Parr, for the lecture. It was really helpful.
You're welcome.
Thank you.
Thank you.